Let's talk about metals, which is actually most of the periodic table. Everything, including lithium, all the way down to osmium and lead, and a lot of the uranium, the lanthanides and actinides. Most of the elements that we know are metals. We even have the transition metal elements, which is the the ones in the middle of the chart, on the D block, and we have the alkali metals, your sodium, lithium, potassium. You have alkali earth metals. So quite a bit of the chart is metals. Now, they can take on a few different shapes, and one of the things that we uh, are going to examine is the unit cell, and that is the smallest possible repeatable unit that we can place these metals into. So if we have that one unit and then we put another one of these cells next to it, another one and another one, that would be the makeup of a particular solid. And unit cells can be for just pure elements, and they can also be used in cases where we have ionic solids. But let's start off with just talking about a pure substance. Now, these are the rectangular cells that exist. There's simple cubic, face-centered cubic, and body-centered cubic. In this one, it's kind of hard to draw, but the central atom here is buried inside of the middle of all of these other atoms around it. And a lot of these other would get in the way, so I tried drawing it there, but it's imperfect. In a face-centered cubic, we have an atom that's on each face of the cube, and then we also have atoms on each corner. And then I probably should have started here, but simple cubic, you have an atom at each of the 8 corners of a cube, and that is cut by just that little slice. And so this is just part of the sphere. Now, one thing that we should do is talk about how many atoms are in each unit cell, because they don't all have the same number of atoms contained inside. So, how do we figure that out? Well, if we look here, starting with the simple cubic, because we'll need to know how big each one of these portions is, because there's also the same kind of structure in this cell and in this cell as well. There's atoms at the corners in each of the 8 corners of the cube. So how much of an atom is actually in there? Well, if we look at this, it would be cutting it this way in half, and it would be cutting it on this face in half, and it cuts it in that face in half. And 1/2 of 1/2 of 1/2 is 1/8. So each corner right here is 1/8 of an atom. And there's 8 of them. So in a simple cubic cell, there's 1 atom contained in it. You might ask why we don't just put the sphere inside of the box, but then it's less easy to see the repeatable structure if we do that. But this is equivalent to just having 1 atom inside of that box. Now, let's do the rest here. So, in this case, we have the 1 atom from all of the corners, so we'll have 1 there, but then we also have half of an atom on each of the 6 faces. So 6 times 1/2, that's 3 atoms on each face. Well, totals up to be 3 atoms from the faces. And then we have an additional one from the corners. So this is 4 atoms contained inside a face-centered cubic. Now let's look at this one. This atom is in the middle of the box, the very center. And so all of it is contained inside of the box, inside of this cell. And then we have, again, our 8 corners making up an additional atom. So this one has 2 atoms inside of the cube. Now, you may be wondering, what is the usefulness of having the number of atoms that we have there? Well, we can actually, if we know what this is packed as, and we know the density of the metal and the molar mass, we can actually calculate the atomic radius based on the size of this cube and how much of the cube is taken up. You can figure that out. And that's kind of a neat thing, to be able to just take a few numbers and knowing what is packing like, and you could figure that out. Or conversely, we could actually figure out how it's packed. And is it simple cubic or is it face-centered cubic? Well, we can actually use the density and the size of that cube, which we can figure out from the atomic radius. So how does the atomic radius relate to the size of each of these cubes? Well, in the case of the simple cubic, it's quite simple. There's one radius to get halfway there, because these atoms touch at right in the middle, and then there's another radius there. So in this case, the radius is equal to 1/2 of the length of the cube. So we can easily determine the length of the cube just by doubling the radius. Now, on face-centered cubic, we're going to have to look at how we can arrive at that information, because these atoms no longer touch directly on one of the lengths of this cube. Nowhere in here. The same thing happens in body-centered cubic, but let's focus on what happens here for now. Now, they do touch along the diagonal right here. So there's 1, 2, 3, 4 radii along this diagonal. Now we can just use the Pythagorean theorem and find out what the relationship is between the length of the side of the cube and the radius, because we know this distance from that corner to that corner is 4 radii, and then we just need a relationship between the length of this line and the length of there. Well, L squared plus L squared equals this length squared. So 2L squared equals that length squared. Well, we'll just take the square root of 2L squared, and we get square root of 2 times L. And that should be the length here. So equals 4 times the radius. So let's see here. In this case, R is going to equal that, right? Because 4 times R equals square root of 2. So if we just divide by 4, we'll get the relationship between radius and the length of our cube here. Now, body-centered cubic is a little bit harder to imagine, so I'm going to try to draw that out here. without all the radii and everything kind of in the way. So here's our cube. Now, they actually don't touch on the face like they do here. They touch from this corner to that corner. So from this corner to that corner is 4 radii. No longer from this one to that one. So we need to calculate the distance between here and there. Well, in order to do that, we'll need 2 triangles. So I'm going to draw the triangle that we used before, and you'll notice right here there's a right angle. So we have a triangle that's right here, and it's at an angle in our box, in our cube, and then we have this right triangle right there. So if we do that, we already know that this length right here, from what we calculated over here, this is L, this is L, and this right here is square root of 2 times L. And we also have another L over here. So square root of 2 squared is 2, L squared is L squared, L plus another L squared, that's 3L squared. And then if we take the square root of that, we'll get square root of 3 times L. That's the distance there. So our relationship between the radius and the length of our cube in the body-centered cubic is square root of 3 times L divided by 4. Because again, it was still 4 radii from this corner to that corner. So now we have the relationship between the radius and the length of our unit cell. And we could use all of this information to find out what the packing efficiency is, or how much wasted space is inside of this cube. And if we were to do that, we would find that the face-centered cubic has the largest or best packing efficiency. So the densest elements will be packed in this unit cell. So some elements prefer to have face-centered cubic, especially the dense ones. Others prefer body-centered cubic. And then very few are simple cubic. This one doesn't show up that much at all for whatever reason, probably because of its packing density.